Hello students, this is the second half of a two-part video series on the multiple choice review questions from chapter 4. We already did questions 1 through 12. Let's jump right into question number 13. In number 13, it looks for two essential features of all statistically designed experiments. So let's look for the things that aren't necessary for all statistically designed experiments, every single one. It's not necessary always to have double blinding. And the reason that it's not always necessary to have double blinding is because sometimes the individuals that you're working on, they would not necessarily be affected by that double blinding. Also, sometimes researchers applying treatments would not be in direct contact with the individuals, so double blinding is not necessary for every statistically designed experiment. We also have a double blinding over here, so we can cross that one off. It makes it a little bit easier for us to pick out stuff that we can cross off right away. In answer D, it says you have to use a block design every time, which is not true. You can have a completely randomized design. That is not a problem. Completely randomized is just as valid as block designs in statistical experiments. And for choice E, it does say to use enough subjects, which is true, but it does always have a control group. That's not necessary. Sometimes you're trying to determine two different treatments' effect on a group of individuals or a group of subjects. So it's not always necessary to have a control group. Sometimes you just have treatment groups. Keep in mind, we're looking for all statistically designed experiments. Yes, all statistically designed experiments are going to compare several treatments, more than one, and also use chance to assign subjects to treatments. This is your gold standard. We always want to use chance to assign subjects to treatments. Otherwise, we cannot determine the cause and effect relationship. Moving on to question 14, the web portal AOL, which makes me feel like I'm 1,000 years old because I'm talking about AOL, has opinion polls next to many of its news stories. So once you read a news story, then next to it, it might have a poll right directly next to it. The question is, do you plan on dieting this year? That seems like a pretty loaded question, and it also seems like if you weren't planning on dieting this year, you might not be inclined to answer the question because it seems like it's shaming you a little bit. More than 30,000 people responded, and 68% said yes. That may be a little high because if you're not planning on diet, it might not be something that you want to trumpet to the entire world. So you might conclude that this is a voluntary response. You don't have to answer it. You're only responding if you feel strongly about it. So the results don't really tell us about the population of all adults. It's just telling us about the people who are motivated to answer this question, right? That's what we're looking for. About 68% of Americans plan to diet in 2008. Well, we have no idea. First of all, we're only looking at people who use AOL, which in 2008 certainly wasn't everybody. And second of all, this is a response sample, so that sample is not necessarily representative of the population. I wouldn't call this a convenient sample because the researchers didn't go into a particular place and choose samples that were convenient. These people responded of their own volition. I would not call this convenient sample. This is voluntary response. The sample's too small to draw any conclusion. Let's be careful about talking about sample being too large or too small until we actually know that for a fact. And none of these is eliminated because the answer is choice C. For question number 15, you're supposed to take a simple random sample of 50 of the 816 students in the dormitory. Here are the entries in that table of random digits, and remember we're looking for 3-digit numbers. We're going to go through this procedure one more time. I showed this in the first video, so I'm going to simply make the underlines for you now. And looking at it here, we're skipping all the numbers that are above 816, so 955 and 929 are out. 400 is the first one, and I got a 769, that's the second one. So my first two are 400 and 769, so it's definitely not 955, definitely not 559, don't know where that came from, definitely not 929. So we have two different options. And we can, before even looking at any of the other digits in the table of random digits, I can eliminate this one because we're trying to get a simple random sample of 50 of the 816 students. We got to skip all repeats. The next one after 769 is 769 again, and then 335. Guess what? It's choice E. For number 16, we're looking at different patients of different doctors, and the study is looking, keep that one in mind, at the medical records of thousands of these patients whose doctors had been whose doctors rather had chosen one of the treatments. All the treatments involved were bypass surgery, angioplasty, and use of drugs, and they determined that the average survival time was highest for folks that were given drugs. I guess specifically, we're talking about heart drugs, not any of the other crazy stuff. The conclusion here to an uneducated person or a person who's not knowledgeable in the ways of statistics might be, oh, drugs prolong life and this should be the treatment of choice. Unfortunately, that is not the case here. What we're looking at is a situation in which we see some sort of correlation, but what we don't see is a random assignment of treatments, right? Bypass surgery, angioplasty, and use of drugs are 3 different treatments in order to determine cause and effect, right? Cause and effect. We need to assign the treatments randomly. None of these treatments were assigned randomly. They just happened to be assigned maybe by certain doctors who were more competent than the others. So we can't conclude that the drugs prolong life. We can't do it because it was a comparative experiment. We can't conclude, so we have to cross this one off. Now, there are 3 different reasons why we can't conclude that drugs prolong life. The patients were volunteers. I wouldn't say that any patient necessarily volunteers to be a heart patient, right? So, and nothing here said that the patients volunteered. No placebo was used. That doesn't necessarily help us determine cause and effect. Remember, cause and effect is based on random assignment of treatment, not based on an observational study wherein there's no random assignment of treatment. The treatment just happens to be what it happens to be. Choice D is correct. For number 17, this question led to such heartache in the years past. I want to make sure that everybody hears this loud and clear. Let's try to go through and analyze some of these answers to cross off some of them. In choice D, it says a sample that doesn't involve strata or clusters. That could describe a simple random sample, but it could also describe a systematic random sample, right? Systematic doesn't involve strata or clusters, so choice D is out. We're looking for one that only describes simple random sample. A sample that's guaranteed to be representative of the population, sorry, there's no guarantees in life, and specifically not when you're doing a simple random sample. It's possible that you get a sample that is not representative of the population. That variation is possible, but it doesn't necessarily guarantee representation if you do a simple random sample. Okay, any sample selected by using chance? Well, that's not necessarily true because in a stratified random sample we use chance. First we stratify into different homogeneous groups, and then we choose from those homogeneous groups in order to make our sample randomly. So any sample selected by using chance? No way. We're down to B and C, and this is where students sometimes get confused. We're looking for an answer that can only be applied to simple random sample and can't be applied to any other type of sampling method. Let's look at B. Any sample that gives every individual the same chance to be selected. Well, that definitely does describe simple random samples. No argument here. But it could also describe some other sampling techniques. Think about it like this. Here I have 2 different setups. The first setup is I'm looking at a big population of 10 individual numbers, and I'm trying to choose a simple random sample of 1 number. It should be pretty clear to you that each of these numbers has an equal chance of being picked. For example, the probability of choosing a 1 here is 1 out of 10. The probability of choosing a 7 here is 1 out of 10. They all have an equal chance of being picked. With a systematic random sample, generally how it works is you list them in order, or you have people come in the door at different times, whatever the case may be, and you select a random arbitrary place to start from, and then you count the same number every time in order to get to the next individual. So I could choose any place that I want to start from here. I could choose the first place, the second place, the third place, etc. And based on where I randomly select to start, I could choose any one of these 10 values. I could randomly select to start at choice 1, I could randomly select to start at choice 4, randomly select to start at choice 9, etc. In that way, all of these values have an equal probability of being chosen. So it is true that a simple random sample follows the definition, every individual has an equal chance of being chosen. But that is not the only type of sampling that follows that pattern. For example, systematic random sampling in this case also has an equal chance of being selected for every individual. Let's go back to the possible choices. Since B is not the correct answer, since simple random sample and systematic random sample both have that, there's only one possible correct answer. Sherlock Holmes said, once you've eliminated the impossible, whatever remains, however improbable, must be the truth. Let's try to analyze why this is the case. A sample that gives every possible sample of the same size, the same chance to be selected. Let's look at it in an object example using simple random sample and also stratified random sample. Let's pick a very similar example to the previous one, but instead of choosing 1 from the population, let's choose 2 from the population. If you choose a simple random sample of 2 from this population, I could get a 2 and I could get an 8. I could also potentially get, oh, I don't know, I could get a 7 and a 9. All of those are possible. And as a matter of fact, every possible combination of two different individuals from this population has an equal chance of being picked. However, back over the stratified random sample, if I choose a odd number, 1, from my strata of odd numbers, my next choice is no longer possible to be, or is no longer able to be, an odd number. It must be some sort of even number. So whereas in a simple random sample, I could choose 1 and 3, I can't choose 1 and 3 in a stratified random sample of 2 from this population. It could be 1 and 2, it could be 1 and 4, 1 and 6, 1 and 8, 1 and 10, but it can't be 1 and 3 because I can't choose from the same strata twice. Therefore, the definition of simple random sample, or the thing that separates it apart from all of the other types of random sampling, is that every possible sample of the same size has the same chance to be selected. Yes, this is true, but it is not exclusive to simple random samples. A sample that gives every possible sample the same size, the same chance to be selected, that is exclusively the domain of a simple random sample. Hopefully, you don't get super mad at me and put a nasty comment on this video, because it's true. Consider the experiment to investigate the effectiveness of insecticides in controlling pests. The best reason for randomly assigning treatments, this one's much easier, this one's a softball. Remember that randomly assigning treatments is a good way of ensuring that we can determine cause and effect. So we're looking here to see if we have anything that says cause and effect. Unfortunately, nothing directly says that. However, remember that cause and effect can be established if we're looking for one cause, which is one variable, and one effect, which is its effect on another variable. We're trying to eliminate any possibility of confounding or any possibility of other uncontrolled factors. Sounds like choice B to me. We're averaging out all uncontrolled factors so that they're not confounded with the treatment effects. We're trying to determine cause and effect by random assignment of treatments, and that cause and effect is not, theoretically, when we randomly assign treatments, is not going to be affected by those uncontrolled factors. Moving on to question 19, the most important advantage of experiments over observational studies, not just because experiment is a cool word to say, it's not necessarily easier to carry out, because when you're doing an observational study, you're just looking, you're not having to randomly assign treatments or anything like that. Confounding cannot happen in experiments. That's not true. We could always have an experiment that doesn't take into account something which could alter the response variable. An observational study can have a response variable in point of fact. Remember that even in an observational study, we could try to determine whether some sort of cause is leading to some sort of effect. We can't necessarily make a statistical judgment on it, but we can see whether there's a cause and effect. And observational studies can definitely use random samples. It's just not randomly assigned by any investigator. The correct answer is experiments give better evidence of causation because, of course, when we're looking at an experiment, we can determine, we can randomly assign treatments, and that helps us determine causation. For number 20, we have some cities, smaller cities, and tiny little towns. We're trying to figure out, or we're trying to set up a situation in which all of these are represented, which means we're looking for a stratified sample from the cities and towns in the market area. Easy peasy. For number 21, bias in a sampling method. Remember, bias isn't just any old error. Bias is a specific kind of error. It's an error that tends to occur in the same direction whenever you use this sampling method. If you go back to the beginning of the PowerPoint or the beginning of this video, you'll see a picture of bias. Check that out to learn more. For number 22, there's a lot of information here, but one important thing is that all your subjects watch the same TV program, but you assign them at random to 4 groups. Those groups aren't blocks, they're not matched pairs. This is a completely randomized design, and the 2 explanatory variables or factors are the ads. For question 23, we're looking for the effect of 2 fertilizers on the yield of soybeans, and this researcher wants to use a matched pairs design. Remember, matched pairs needs to have pairs that are as similar as possible, so that means they're going to have to subjectively divide these 20 plots into 10 pairs, making sure that those pairs are as similar as possible, and then flipping a coin. That's your classic matched pairs. And last but not least, whenever you're mailing out a survey to people and looking at people who responded, we're looking at a potential for non-response bias. This was the video on Chapter 4's multiple choice review. Good luck studying.